This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So we started the Brayton cycle analysis yesterday, and the Brayton cycle is one type of gas turbine cycles. And the purpose of Brayton cycle, or the application of the Brayton cycle, is mainly to describe how a power plant works using a gas turbine. So the useful output of this process is the shaft work, right? So that's different from the things we are going to discuss probably tomorrow, which is for the aircraft propulsion. So shaft work is a useful output from the Brayton cycle. And we mentioned that the basic Brayton cycle is basically the three components, consists of 4 steps. And we're dealing with ideal cycles. So by ideal cycle, I mean these few things here. Reversible, no any losses in terms of temperature or pressure. And we're only dealing with air as the only working fluid, and it is treated as ideal gases. So ideal gas relation, that can be relations that are applicable for ideal gases that can all be used, including ideal gas law, including the isentropic relation. And then also consider the air has the constant properties, right? So we derived the work term, compressor work, for the first step from the last lecture. So we know that from 1 to 2. Right, from 1 to 2, if we apply the first law, and because we consider isentropic process is by definition is an adiabatic process, so this one goes to 0. Then we have the compressor work, which is equal to the absolute value of the work from state 1 to state 2 equals to the Cp T2 minus T1. As said, all this work and heat term we're dealing with here, that's the we're dealing with the absolute value, right? So they are not necessarily corresponding to the end state minus the starting state. We only dealing with the absolute value there, right? So that's 2 to 1. And the temperature at the state 2 can be calculated using the isentropic law. So based on the pressure difference at the inlet and outlet of the compressor, which is typically given as a value of the pressure ratio, or RP, then we can determine what is the end state temperature for this after the compressor. So we can calculate how much work the compressor has done for the ideal step. Then the 2 to 3, that's where the heat being added. Again, starting from the first law. Right, and in this case, basically, we consider it's air-only process where the heat being added externally to the working fluid. So there is no work being done by the fluid in this process. There is no any useful shaft work being outputted. So this case, the work goes to 0. Then the Q in equals to the Cp T3 minus T2. Right, and then the turbine step. So where we have the similar thing, we can write the Q minus W equals to Cp T4 minus T3 So again, turbine is considered as an isentropic device, ideal process. And so the Q will goes to 0 again. Then we have the turbine work equals to Cp T3 minus T4. Positive value, T3 higher than the T4. So we're dealing with positive value of the turbine work. And then the last step is 4 to 1. Then the Q so again, this process is a constant pressure, and then no work being done. Then this one goes to 0. Then the Q out equals to Cp T4 minus T1. This should be straightforward, and that should all coming from your previous learning. Apply the first law. That's the very first step to doing this kind of analysis. All right, so we figure out the 4 energy terms involved in the 4 steps. We want to know the efficiency, right? So all the cycle analysis is the primary target is to figure out what's the thermal efficiency of the cycle, and then how to improve that efficiency. So if we write the efficiency of a Brayton cycle, the thermal efficiency defined by the useful output versus the required input. The useful output is the work. And here we have 2 work terms. We're dealing with the net work. So that's WT minus WC divided by the Q in, which is a heat transfer that drives the process to happen. All right, so we can do the similar way, equals to Q out over Q in. That's something, basically the net work equals to the net heat transfer. Right, so if we do that, we can bring in the energy term we derived here. So that will be Cp T4 T1, Cp T3 T2. So this is coming from our analysis just above. The Cp cancelled. Again, consider we're dealing with the ideal case air only. The air has a constant property. The Cp in reality is a function of temperature. So in general, it's actually going up with temperature. But here we treat it as constant. Then we have a little bit mathematical trick here. So we using we have T1 outside the parentheses, then have T4 over T1 minus 1, then T2 have T3 over T2 minus 1. So this is no problem, right? So I just have the T1 as a common factor out of the parentheses. Then the next step is we find some relation which can simplify the equation here. So if we consider the isentropic relation applied to the compressor and applied to the turbine. So on the compressor, we can write T2 over T1, the compressor outlet over compressor inlet, should equals to the pressure outlet, pressure inlet, following the isentropic law. Right? We mentioned that the cycle, not only this gas turbine cycle, later on, when we're looking at the refrigeration and the steam turbine, basically all these cycles are working between 2 pressures, a high pressure and a low pressure. So particularly here, there is we deal only with 2 pressures. So the P2 has the same pressure as the P3, and the P4 has the same pressure as a state 1. So what I can write, just have the P3 over P4 right? So because it's two isobaric process during the heat addition and heat rejection. And then this one becomes to what? Becomes to T3 over T4, right? The turbine inlet versus turbine outlet. So if we recognize this equals to that, we can simply rearrange to get the T4 over T1 equals to T3 over T2. So if you're looking at the term we derived here, so that's saying this and that are the same, right? So basically these two got cancelled because they are the same. So then we simplify the efficiency to become 1 minus T1 over T2. So the turbine inlet versus turbine outlet. If you recall the expression we discussed on the Carnot cycle has a similar form, except for Carnot cycle thermal efficiency, it would be 1 minus T cold over T hot. So that's different from here. Don't get confused with that. This one is a compressor inlet versus compressor outlet. But we can just simplify it. 1 over Rp to the gamma minus 1. Because these two should follow the isentropic relation. So the pressure ratio to the power of gamma minus 1 divided by gamma. This relation is the efficiency term or efficiency equation that we derived for ideal Brayton cycle. Here you can directly see that if you increase the pressure ratio, increasing pressure ratio, this denominator will become higher, this negative term will become smaller, then the efficiency will goes up. So we'll come back to that in a minute. So this is an equation that basically we derived for the ideal Brayton cycle. The next, so this is the basic cycle. Our main focus is actually how to improve these basic cycles. So in terms of efficiency, if I draw a TS diagram, so from our previous discussion on the Carnot cycle, we mentioned that certain area on the TS diagram can corresponding to a certain energy term. So for example, if we dealing with the Q in here, the Q in is for reversible process can be written as the TdS. For reversible process, the heat transfer equals to temperature times changing entropy, right? Reversible process. But this is a global term. This is a differential term. We need to do the integration. So the integration will be from the state 2 to 3, right? So in this case, temperature is not constant, so you don't have a straight line to deal with. But still, if you do the integration, you would have the temperature times the differential change along the entropy axis. Then you will have this total heat. And that total input heat equals to the area underneath this curve, temperature curve, right? So if I call A and B, that equals to the area of A, 2, 3, and B. right? So similarly, the Q out can be written as from the 4 to 1 TdS, and because the 4 to 1 will be a negative heat transfer, so I put a negative sign there to make it to be positive. Then corresponding to the area of A, 1, 4, and B. So the difference between these two will be this irregular area closed by these 4 steps. So the area, the net work, which is the difference between the turbine and the compressor, that would equals to the area of 1, 2, 3, 4. All right. So this is the area we are interested. So as I said, the efficiency basically is the area of 1, 2, 3, 4 versus the area of A, 2, 3, B. So this area versus the total area underneath this curve, right? So if we want to improve the efficiency, we want to enlarge this work area and do something to achieve that target. So if we can, basically 2 ways we can do that. One is we can if we can lower this lower curve, all right? So if we can 4 to 1 can be dropped lower, then this area will be, the work area will be larger, but the total heat Q input will be no change, right? So we'll get high efficiency because this area, work area, accounts for a larger fraction of the total heat, total energy input. Or we can do, you can raise this up, raise the high temperature part up. So in this case, the work area become larger and the heat input also become larger. But definitely you can see that the fraction of the work is increased. The fraction of the work in the total energy input is increased because the additional area is all work, right? Additional area is not no waste in terms of the heat, dump the heat to the low temperature reservoir. So you can do 2 things. So I should say, to improve efficiency, so either reduce temperature from 4 to 1. But this measure actually is not really practical. If I want to lower this lower curve, it's not really practical. An idea on why? Pressure drop. Yeah. Pressure. Yeah, the pressure will be lower. Compare this curve. As I said, this is a constant pressure line. This is a constant pressure line, right? Again, constant pressure line. This lower line will corresponding to lower pressure. So, can you change the pressure of the ambient? Not really, right? If the aircraft if a gas turbine is running on the ground to produce electricity, you cannot change the ambient. Drop the pressure, meaning you need to drop the ambient pressure, which is not really practical. So that's the case. You wouldn't be able to drop this line very much. So need to drop ambient pressure. Which is not really practical. So the other one is to increase temperature from the 2 to 3. So this one basically saying that during the heat addition, first you compress to high pressure, and then you add the external heat at higher pressure. So this curve can proportionally goes up. So this is possible. So this is actually not only possible, that's the major measure to increase the thermal efficiency of the Brayton cycle. So people already recognize that if I can raise the temperature of the stage 3, which is corresponding to the turbine inlet temperature, so if we can raise the turbine inlet temperature even a little bit in terms of efficiency, I'm going to gain some. So this has been long recognized. Actually, it's already been almost developed to the point you cannot increase much. So there is a plot here which could be interesting. So this plot is showing that over the years, the hot turbine inlet temperature has going up and up, and how different technologies has been used to enable that temperature rise. So it's going from 1965 to somewhere around today. So initially is a temperature around 800 degrees C. When people applying different technologies, nowadays it can reach somewhere around 1600 degrees C. So 1600 degrees C is it's a very high temperature. So a flame or combustion temperature is typically around 2000 Kelvin, which is around somewhere around 1700 degrees C, right? So it's close to, we are directly getting in contact with the flame. So this is achieved by using different technologies. So basically showing as a curve here. One is due to the using more advanced alloys. So this basically corresponding to this brown curve. It allowing you to go from certain temperature to somewhere around 900 C. But this one is not, you cannot go too much higher because at some point the material will melt, right? Getting close to the, you cannot getting close to the melting point. Where before the melting point, the material will start to creep and then lose its strength. So this is one is limited by the materials, and then you can do something called thermal barrier coating, TBC, thermal barrier coating. Basically, you can coat certain material which can resist the high temperature, basically to protect the metal. So that's actually is showing the, here I don't know if we can. So this is diagram showing that there is different multi-layer material being applied to the metal, which is the metal substrate here, and then you have multi-layer being coated on top of it to protect the, so this material typically is ceramic. They can handle high temperature. So that's one technology. I should say that's the second technology, the material, the thermal barrier coating, and the other one is the called advanced cooling. So the blades nowadays actually being designed in a way it's being effectively cooled. You have it's not an ambient temperature air. The temperature is still air is still pretty high, but certainly it's nowhere close to the combustion temperature. But this air is much lower temperature compared to the turbine inlet temperature. So they're being flowed inside the blades, and as well as you have the small cooling holes. So the air can coming out of those three holes. They are not coming out as a high velocity jet, coming out at a relatively low velocity, and they can stay near the surface and to form something called a film cooling. You form a film air which is on top of the surface to basically to isolate the high temperature from directly coming from the combustion outlet. So that's different technologies already being used to allowing the temperature goes to close to the flame temperature. So from our discussion here, basically it's become less a thermodynamic problem than a materials problem and then a heat transfer cooling problem, right? But that's something we want to be aware. That's a major measure that has been taken to raise the thermal efficiency. Protected by thermal barrier coating and advanced cooling. All right, so that's the again the major measure which almost being used to its extreme. And there is several other ways we can also increasing the Brayton cycle efficiency. But given the temperature is nearly turbine inlet temperature nearly reached the limit, so for our further discussion, we need to consider that there is a threshold being put on the T3. So that's the TS diagram I'm going to draw here. So let's say we already reached the threshold for the turbine inlet. Then we can have multiple ways to realize our cycle. 1, 2, 3, 4. So with the T3 being fixed and with the inlet being fixed, basically that's the ambient temperature and ambient pressure. So we still have different way we can operate between these 2 points, right? From here to here. So this is one way. I can do this in another way. So if I call this one as 2 prime, 3 prime, and 4 prime, or I can do it in another way. Double prime, 3 double prime, and 4 double prime. So between the starting point and the threshold turbine inlet temperature, I can still have various ways to design my gas turbine cycle, right? So they are different in terms of the efficiency and in terms of the useful output they can produce. If I ask you which case has the highest pressure ratio? Single prime, no prime, double. And the reason? Higher, longer distance from state 1 to the end of the compression? Okay. That's temperature. How do you know the temperature difference with the pressure difference? Yep. Okay, so that's good. So that's correct. This single prime case has the highest pressure ratio. So in terms of pressure ratio, I can say 1, 2, 3, 4 single prime higher than 1, 2, 3, 4 higher than 1, 2, 3, 4 double prime. And the reason is the temperature difference here, a larger temperature difference corresponding to a larger temperature ratio, right? A higher temperature ratio corresponding to a higher pressure ratio because they are limited by the isentropic law, right? So that's correct and good. So this case has the intermediate pressure ratio, and this case has the lowest pressure ratio. And which case has the highest efficiency? If we're looking at this, at least the two ways you can tell which is more efficient. Yep, higher pressure ratio, higher efficiency. And can you tell from the TS diagram? Which area corresponding to work? The area enclosed by the 4 steps, right? They have different work. That's obvious. But they also have different heat input. Heat input corresponding to the heat that you add here, and add here, and all the areas underneath this curve. So if you can tell this work area in terms of fraction accounts for a larger fraction of the total area underneath this curve, then you should have a more efficient cycle. Is that clear? So let's pick this one. All right. This is the 1, 2, 3, 4. That's area. That's the work, and the efficiency. You can directly tell from the fraction of this work over the total area underneath this curve, which is corresponding to this area. So you should be able to tell for the single prime case, the work corresponding to this much, and the total area is this much. So the heat being rejected accounts for a smaller fraction in the total. Compared to the other extreme is this. You have a work corresponding to there, and you have a large amount of heat being rejected. So that's also consistent with the analysis or the equations that we derived earlier in this lecture. So by two ways you can figure out the efficiency should be consistent with the pressure ratio, 1, 2, 3, 4, single prime. Right. However, a higher efficiency does not mean the cycle can produce a large amount of work. So if you're looking at the absolute work that's being outputted from each of these cases, I can tell that the case without prime produced the most work, certainly higher than this single prime case, and it should also higher than this double prime case. So the work output is different, and the work output is not consistent with the efficiency. Is that sounds inconsistent with the efficiency? If you have if you understand that high efficiency will corresponding to high amount of work output, that's based on assumption that the input heat are the same into the cycle. But for these cases, they have different heat input into the cycle. So even this case without prime output a higher amount of work, it can be less efficient. But for certain cases, yeah, go ahead.
Actually, I want to ask, mostly we calculate on the ideal conditions. Actually, how certain our result will be like the real world gas turbine. Because we calculate in the ideal gas, no pressure loss, and etc. Like how certain our results compared to the real gas turbine?
Yeah, so that's, if you want to know that, you consider what's the difference between the ideal cycle and the practical cycle. I mean, the things we consider here as the ideal condition, what can cause losses? The heat can be lost, pressure can be lost, which means you have friction, which means you have to run your compressor harder in order to create the same amount of pressure ratio. And also you have the inefficiency caused by the combustion process, which means the combustion is not necessarily 100% complete. So in terms of the number, you can consider that the ideal cycle cannot be more efficient than Carnot cycle, right? Because now this cycle, Brayton cycle, is not a Carnot cycle. It cannot be more efficient than a Carnot cycle. So that's its limit. And then you account the different source of non-ideal conditions. Then you can get the actual thermal efficiency. So for typical Brayton cycle, I would say in reality, just around a Brayton cycle, its efficiency would be no more than 30%. But as we will say later in the chapter 4, when we're talking about steam cycle, you can combine a gas turbine cycle with a steam cycle, then create a very efficient process, somewhere around 60% in terms of the input and output work versus the input energy. All right. I guess what I'm trying to say here is, in terms of efficiency, yes, this is a single prime case is more efficient, but in terms of work output, that's not. So the case of without prime is higher than the, let's say, is 1, 2, 3, 4 double prime, and higher than the single prime case. The net work output can be very important and can be critical, because that's saying that when I run my engine for one cycle, for example, let's assume the different cycle running, complete a different cycle with a fixed amount of time. So with a fixed amount of time, if I have an engine, even it's less efficient, I can deliver more work, which means I can deliver more power for the engine. So in terms of the power density, I win. So even the engine is less efficient, I can deliver more work per time, per unit time. Then I can have a small engine to deliver a large amount of power. So that's useful particularly for transport and particularly for aviation transport. Right. So for certain cases, the net work output is the performance you're after. For other cases, the efficiency you're after. So depending on your target, you can choose between the single prime case and the without prime case. All right. So there is a tutorial problem which you will learn how to determine the pressure ratio, which corresponding to 1 to 2 without prime case here, can give you the maximum work output. So that's I can write the results here, but you can derive in your tutorial problem. The maximum net work output is with the pressure ratio equals to T3 over T1 gamma 2 gamma minus 1. Okay, so this one saying that if you set the pure pressure ratio at this value, you can have the maximum work output. Certainly not necessarily the highest efficiency case. And another thing you want to be aware of, if you really after high efficiency, it's not saying it's economical or it's wise to design a system with super high pressure ratio. So if you plot the equation we derived earlier, so if you plot this equation, which is efficiency as a function of the RP, you will have a curve like this. So if the pressure ratio is really low, you're increasing the pressure ratio, you can gain the efficiency quite a bit. But when the pressure is really high, then it's kind of leveled off. So the gain is called diminishing return. So at a higher, very high pressure ratio, actually you do not gain as much as the one you had a lower pressure ratio. And the high pressure system actually is quite expensive. So for industry, high pressure means more expensive because everything has to be built to handle that pressure. The pressure is equilibrated quickly everywhere. So that's not necessarily justify the high cost in the first place. So increasing pressure, the diminishing return on the efficiency increase. All right, but nonetheless, going higher pressure ratio, that's in terms of direction that can give us a higher efficiency. That's something we want to be aware of. Another thing we can improve the Brayton cycle efficiency. That's related to some non-ideal conditions in reality. That's which actually related to the question being asked just before. So that's to improve efficiency of the compressor and the turbine. So in our ideal cycle, we consider these two devices 100% efficient, but in reality, certainly they are not. And there is a definition, isentropic efficiency that being defined for each of this device. So in terms of the compressor, the isentropic efficiency is defined as the actual work, the case for the isentropic process versus the actual case. So the S stands for the isentropic and the A stands for the actual. So it's saying that you always need to do more work than the isentropic ideal case in order to reach the same pressure ratio. So in this, one can be written as the T2S minus T1 or T2A minus T1. So we need to mark it on our. Okay, let me just draw it again. So in reality, you go a process like this. This is your 2A, and the vertical line corresponding to the 2S. And the ratio between this larger temperature versus the isentropic case will give you the compressor efficiency, which is always smaller than 1. And similarly for the turbine is the opposite. What you can get is always less than the ideal case, right? You actual work delivered by the turbine versus the isentropic case. So there you would have something like this. So that's this our 4s and this our 4a. So this case, isentropic case, will be replaced by this actual case. You would have the T3 minus T4a versus T3 minus T4s. And again, this must be something smaller than 1. So they are relatively efficient in compared to an engine, I should say. So their value is typically around 80 to 90%. But any improvement you can do with for these two devices, you can improve the efficiency for the overall cycle, right? So that's that. Another two processes or two measures that we can do, actually it's more commonly done in reality, is to change the basic cycle, basic Brayton cycle, by adding components to this basic cycle to make the process more efficient. So that's what I'm going to discuss next, and probably only got time to finish one. So another measure to improve the efficiency of the Brayton cycle is a process called regeneration. So the regeneration, in terms of the schematic, you have a compressor, combustor, all right, so that's the same as the basic cycle, but the difference is the exhaust coming out of the turbine is not directly dumped to the environment. You put a heat exchanger, which essentially a heat exchanger, but we call it a regenerator here. So the hot exhaust coming out of the turbine going through the heat exchanger, this direction, and heat up the air which is leaving the turbine, leaving the compressor before it going into the combustor. All right. So this one is called the regenerator, and this is a device which is very effective in terms of improving the efficiency of the cycle. So if we draw it as 1, 2, 3, 4, 5, and 6. All right, we can draw the TS diagram. So we have a new component in the cycle. So I want to draw it carefully because there is a certain state and one needs to be higher than the other. So if this is a 1, all right, the inlet, then the after compressor 2, then before going into the combustor, it is going through a heat exchanger to pick up some heat, so it will gain some of heat, go to the state 3, then go to the combustor to go to state 4. Then after combustor, go to state 5, and then before it getting into the environment, it will give in some of the enthalpy to the compressed air. So I have it here. State 6 before it goes back to the environment. All right, so that's like this, and this. Let me just put a few. All right. So why this process can improve the efficiency of the cycle? So here, if we're looking at the thermal efficiency in this case. The total work, total net work, right? The total net work has no change. The total net work is still corresponding to this, the area enclosed by this now 6 steps, 6 states, 5 steps, right? Still corresponding to the area of 1, 2, 4, 5. But the heat, the Q in now is coming from only from the state 3 to state 4. Because from 2 to 3, that corresponding to the exhaust heat from the turbine, you only need to add heat to raise the gas temperature from state 3 to state 4. So that's where your Q in is. So this one is going from the Cp T4 minus T3, which is smaller than before. Smaller, previously you have to go from 2 to 4. Now, some part of it is being saved due to you are using the exhaust heating, right? So this term goes down, and this term does not change. So the thermal efficiency must goes up. So that's the principle. The regeneration process can help in terms of efficiency by looking at the TS diagram. And when you looking at the diagram, there is the things happening in the regenerator needs to pay attention. So in this case, if we consider the process is ideal, which means there is no heat loss, so all the exhaust heat, which coming from the state 5 to state 6, will be given to the compressed air. So in terms of energy balance on the regenerator, you should write Cp T5 minus T6 should equals to Cp T3 minus T2. So that's the energy balance that you need to apply for the heat exchanger. And often when you solve problems, that's an additional equation you need to know and to use to solve the problem. All right, I think that's all for today. We'll discuss another process which involving the regeneration on Friday. If I just follow the first law, it will give me a positive value in terms of work.
Oh, okay.
Because again, the system output work we consider that's a positive work.
Okay.
But for compressor, it's a system is the work being done to the system.
Okay. Thank you. Where did the regenerator get its power to rise the temperature?
So it's coming from because this exhaust temperature.
Yes.
I mean, if you don't have it, it will be here, right?
Yes.
It's a high temperature than the initial.
Yes.
Higher temperature even than this temperature of the compressor. If the system being designed correctly.
Yes.
So that you can use that basically this stream still hotter than this stream. So you can just transfer using a heat exchanger to transfer the internal like some energy from it.
Okay.
Yeah.
So this part and this part is.
Yeah. So
yes.
this,
Yeah.
Because our stream
the
is
difference
hot.
in heat. Yes. Okay.
Yeah.
Okay. Thank you very much.
Successfully contact Dr. Gordon, and maybe I will make some sexual suggestions. Yeah, okay. Yeah, that's right. That's right.
Cycles yesterday, and correct me if I'm wrong, but these processes